Okay, so let's talk a little bit more about recursion. The first thing I wanted to go over was this example that I posted on Canvas yesterday. So let's just say we wanted to write some code that reversed a string. Then there's really two ways we could go about doing that. Or at least I think two common sense sort of ways. So we could either start with some string. So here you'll see that, and I'll write it out in a second, but you'll see that we start with some sort of string, and then we have two different versions for reversing it. So for the first one, what we do here is we take the string itself and we append the character to the end of it. So here we start at the end of the the string, and kind of work our way backwards. So while I is greater than 0, I minus minus. So it starts at the end, works its way back. In fact, that should be a -1. I think I made a mistake, but it ended up printing out okay, so I guess it's not a big deal. So it starts at the end and then kind of works its way back, versus this other one, which will do the opposite. So let's just go over kind of the execution order for this one. So I'm just going to write the pseudo code here. So we have basically for length -1 to 0. Then what we do is we take the string itself. So let's just say str, or actually I guess I call it reverse 1. Let's keep it consistent. So reverse 1. Reverse 1 is equal to itself plus the character at the end. Plus, so we had some kind of string, and in order to access it like an array, we do something like this. Okay, so let's maybe go up here really quick and write that string. So we had that str was equal to the string hello. So if I write that all the way out, then if I was to treat this like an array, this would be position 0, position 1, position 2, position 3, and position 4. So we start at length -1, it will start at 4, and then work its way towards 0. So this execution right here, it will start with string at length -1, which is O, and then it will copy the L, the E, and then the H. So if I was to go through letter by letter, then what this is first is it's O, and then it's OL, and then it's OLL, and then it's OLLE, and then it's OLLEH. Right, so the idea with this one is that it starts at the end of the string, works its way back. I don't know what annotation does, but I'm sure. Start annotating. Oh, maybe that affects my thing. Okay. Let me see if I can turn that off. I thought I was gonna let it on your end, so I was just gonna do that. Let me try turning that off. Sorry about that. But this ends up going kind of backwards, right? It starts at this end and then works its way backwards and then kind of appends to the end of this, right? So at first, reverse 1 is nothing, and then it gets the O from the end, and then the OL, and then the OLL, and so on and so forth. Now, the other way that we could do this is, so the first way was we kind of start at the end of the string and then work our way backwards, which I think might be the most common sense way to do it, but there's another way we could do this, which is we could do for, and then we could start at the beginning, right? So we could say for I equals 0, yeah, let's just say I equals 0 to length -1. So the way you normally write an array traversing, right, is just to start at 0 and then go to the end. Actually, I guess at this point it would be to length, but yeah, we'll do that. And then what we could do is we could say that the string that we want, reverse 2, is equal to, and in this case we would have to go the other way around. So if I did something like this, where I say string sub I plus reverse 2. I think I misspelled that. I put 2 E's and 2 V's. Can't spell. Alright, there we go. Reverse 2. So if I did it this way, then again, if I had the same sort of string here, str equals hello, then this one would go from the starting point, which is 0, until the end. So if I was to execute this one, again, we just say reverse 2 starts as just an empty string, and then here it would take string sub I, which starts at 0, and append that to itself. So first it's going to take the H, which is in the first position, and then the next thing it's going to do is it's going to take the next character, and it's going to append it. So you can see here, this is the front of the string, this is the back of the string. So it will append it to the front, and then it will take the H from the last step. So let's say that this is the red part here, and this is the blue part. And then on the next step it would, so let's just throw this out here. So it's going to go in order, right? So it's going to go from there to there. And every single time it's going to append the string from the last time. E-H. So this would be here when I equals 0, I equals 1, I equals 2, I equals 3, and I equals 4. Right, so it always takes the next string in the sequence here, and then appends the one from the last level above it. So you can see here that this EH is the same one as that layer, and then this HEL is the one as that layer. Is that clear so far? These two different ways that we could reverse a string is to, in one way, go forward and then kind of append a character to the beginning, and then the other way would be to start at the end, work our way back, and then append a character to the front. So maybe here, if I did that, then this would be O. Actually, I guess nothing in the first layer. O, O-L, O-L-L, O-L-L-E. So where that red part is the line above it, which was the string from the last layer. So what I want to do now is try to do this maybe in a recursive fashion. That way we can figure out maybe a way that we could reverse things, or again kind of traverse a list. So we did an example of how you would do a for loop with recursion last time, but let's maybe do a little bit more of a practical thing where we actually kind of simulate this for loop and do something inside of it. And we'll try to do it both ways. So I guess there is a way to do it similar to that, and then a way to do it similar to this thing here. Right, so let's try to do this one first. So on this one, the idea was that we traverse from length -1 back to the beginning, and that we are going to take the string so far and then append the next character to it. Right, so if we wanted to do this, we probably want to have some sort of function called reverse. Let's just call it rev. And we want it to reverse a string. Let's just say some string s. And I suppose it would be helpful to have the index as well. So let's throw out int I here. And then we'll try to do it. So last time we talked about two things that you need in every single recursive like scenario you have. Does anybody remember what those two things were that we have to have? It's okay if you don't remember the name, but does anybody remember the general idea of what we had to have? A stopping point, right? an end condition. Fair enough. A base and an update. Okay, yeah, right. So I think you all are on the right track. So we need some sort of stopping point, and yeah, that's called a base case. So our stopping point here would be what? So what's the index that we stop on for this one, or what's our base case? I equals 0. Yep. You guys are both right. So we know that if I is 0, then we're good, right? So when I equals 0, maybe we'll just take this case here. So I didn't actually write out the indices, but I equals 0, I equals 1, I equals 2, I equals 3. So it looks like when we have that individual I equals 0 case, then what we maybe want to return is just a individual character. And we could also do this another way where we say I is less than 0 and return the empty string, and that would be alright too, I would say. But yeah, let's just do it that way. So rather than return an O directly, we know that's not always going to be the case, right? Because we might have a different string. So let's just return S sub 0 then. So return... I didn't actually give this a return type. I suppose I should. Ooh. Hope I actually wrote out the whole thing. So let's return the character at position 0. I said public. Wow, I've been writing too much C# over the weekend. We want this to return a string, right? So, string. There we go. No, that's C++. But anyways, this was, like we were saying, this is the base case. So it's kind of a stopping point, or a beginning point if you want to view it that way, which is usually the way we view it in math. And then we needed another thing here, which was an update, or in other words, some sort of reduction. Some sort of way, I guess, to make the recursive function approach that stopping point. So we need a stopping point, and then we need a way to get to it. So in that case, I think the most common sense way, so I didn't write out the full for loop, I was just doing pseudo code. But if you were to write this in C++, you would do something like I minus minus, right? Or, in other words, I equals I minus 1. And so the reduction there is subtracting by 1. So what we'll want to do is we will want to apply this same function and then kind of append the character. So we have to be a little bit careful here. We know we want, if we look at every single case here, we want to append this character. I guess we're kind of starting this way now. We want to take the string, so this is the rest of the string, right? And we want to append it to the leading character. And so you'll notice here, so this is the string of size I minus 1, and this is the string that's just the leading character, so this is a str sub I. So it appears that I want the reversed string on the left-hand side. So this part, I guess right here, the thing to notice is that it is reversed. If I think of this answer backwards, which you usually should when you're doing recursion, is the red part here is the reverse string, which is kind of what we have in this above thing, right? And then the part on the left is the current character. So what I want to do here when I return is I'm going to return the reverse on the left, which is a call to this function itself. So part of understanding recursion is knowing what the function itself is supposed to do. So the function is supposed to return a what's it called? A reversed string. So it's supposed to return S reversed up to some index I. So maybe I'll do this in green here to the side. Rev returns the string S reversed to index I. And this is what you might consider, if, I don't know if they went over it in 135, but this is what you might consider a post condition, which is a condition which is true once the function returns. So we always expect this to be true whenever the function comes back and gives us a result. And it's kind of important to consider this when problem solving, because I think it helps quite a bit to think about, well, I might not necessarily know how the function works, but this is what I expect it to do when it's done. And so what we expect it to do here is return that reverse string, which is this red part up there. So what I want to do is call the function, which is supposedly supposed to give me the reverse part, and then I will call it with s, and then we said earlier that in the loop we would do something like I minus minus, which would be I minus 1 here. And then we need to append the current character to the end of it, so we would say something like s sub I. And I could definitely do this as a length as well, in which case we would need to subtract these, or subtract this by 1 and then make that if I is -1, and then subtract it that way. But we'll kind of keep it like a for loop. So this was that red part, so this is the reverse string, or the reverse 1 that I had in my for loop. And then this was the character. Any questions on how we implemented this one? Or why we did it in that specific order? I know it's probably hard to see all this stuff all at once because I have so much written down. But if you have any specific questions. Alright, stop me if you do. I'm just going to go over to the other one. So the other way was to do it the opposite way, where we start at 0, work our way to length, and then we work our way up. So actually one last thing we should probably throw down here is how we would call this one. So we would call it reverse, and then we would give it the string, and then we would start at length minus 1. So this one started at the end and then worked its way up. Whereas this one we're going to call it with 0 in order to do it correctly. So this one, in this case, is taking the character and appending the reverse string. So let's do string, let me give this a different name. So I called this rev. Let me, just because I know where I'm going with this, let me call this rev h. I'll explain what the h is in a second, but we'll call this one rev t. And again, we'll take some sort of string s and index I. Maybe go a little bit over. All right. All right, so again, what do we maybe need for this function in order for it to work? And actually, maybe there's something tricky about this. If we take a look at the other one, so again, for recursion, we're always going to need that base case, and then we're going to need, I didn't write it, but we're going to need some sort of reduction. Right, so the trick about this one is that it actually goes from 0 to length, but we don't really want that, right? So we have a bit of a, we're a bit stuck here. We want to go and ideally reduce it, but I suppose we're going to have to go the other way. So in this case, our base case is actually not going to be a small number, but rather the big part. We want to stop when we hit the length, right? And the convenient thing is we actually do have that because there's a way to check the length of the string s. But when doing recursion, it usually makes sense to go this way and subtract. But we'll work with it. So our stopping point on this one, we know wasn't 0, but rather was the length itself. And we'll just say length -1 since we're working with these indices here. So if I is equal to s dot length -1, so in other words, if we've reached the end of the string, then we know we want to return the base case there. So once we've reached the very end, we want it to return that O, which is the string at the very end. So we will then return S sub. And we know I is equal to that, so I think it's just easier if I put I rather than get the length again, because that would be inefficient. Did I put return on that one? Yeah. Okay. Right, so this is our base case for this one. We want to stop at the end instead. And then so the name here on the second part might seem a little bit confusing at first, because I've been calling it a reduction operator, but we're going to do it a little bit different here. So I'm going to want to do for my actual return case, I'm going to need to do, in this case, I'm going to need to do the character and then the reverse string after it. So the character being si, and then the reverse string being when I call the reverse function. Since again, we know its condition is that it's going to reverse the string, then I expect this to work correctly and actually reverse it. And I'm going to call that on S. And what do you think I'm going to put here for this one? So what am I going to do for this reduction operator? On the last one I was subtracting by 1. And I guess that makes sense with the name reduction. Maybe another way of phrasing this is, if I was to actually write out this for loop, what would be the thing at the end? So what would be the like end of the loop statement? So if I wrote this one all the way out, you might do something like for int I equals 0, I less than length I plus plus. Right? Hopefully that makes sense. If I'm going from the beginning to the end, I would typically go I plus plus to make it go upwards. So here, if we're trying to reach the end, which is a bigger number, then what we want to do is actually call this with a number that's 1 bigger. So I plus 1 here, we'll say. Which might seem a little bit strange since I'm using the name reduction. In computer science, the name reduction doesn't always actually mean make smaller. Although I typically think that's a better way to think about recursion. That's not always the case. In fact, when you start talking about complexity of problems, maybe you'll see that when you reduce a problem, sometimes you actually add things to it, which might seem counterintuitive, but I suppose that's just the terminology. Okay, but is that all right? So we have another reverse part here, and then the character. So this should also reverse the string. Did you want me to program this, I guess? Or is it okay if I just kind of write this here? You think it's okay? All right, fair enough. I mean, if you want to program, just, if anybody wants it, just let me know, and I'll write it out. Okay. So the difference between these was that we call the reverse first and then the character, versus on this one where we call the character and then the reverse. Let me do a new thing here. So I had these two cases, and then this one was, this one should have been the I plus 1, right? Yeah. And then I had the other one, maybe it makes more sense for me to put it down here, where I took the reverse string first, and then I did -1, and then I add the character to the end of it. So this was rev h. This one was rev t. And they both did the same thing, really, right? The only difference was where we added the character. So on one, we called it here, was where the character was, and then the function call was on the left, and then here, the character is on the left, and the function call is on the right. So there is a bit of an actual difference in terms of these when we start doing more complex problems. And we have names for these ones. So this one here is called tail recursion. And this one would be called head recursion. And the difference lies in where the function call that actually does the recursing is. So here, the function call is on the second half of it, hence the tail part. And on this one, the function call that does the recursion is the front part, so it's the head. And really the difference there is kind of the way that the functions end up executing. So let me just grab this really quick, and we'll move it to a new page. Can I move this around? No, I think it's just kind of stuck there. Let me move this to the corner. No? I don't know if there's an easy way to like move this around. Add to library. Oh well, we'll just move. So if I take this first one, yeah, this is okay. When I do it, so let's just say I call this, oh, that doesn't help. All right, well, that's gone. Let's just start at the beginning. So with the first one, we had C plus, I guess I'm starting it with it kind of backwards, but this was the reverse T, and then what we did is we called it with the string hello. And for this one here, we called it with 0, right? And then we did I plus 1. So as far as the execution, this C that we started with would have been the character at position 0, which was H. O. No, that should be O. I'm doing the first one. Just tail recursion. Right, so we would have... Am I making a mistake with that? I plus 1. No, it did start with O. Okay. Right, this started with 0, H. I'm sorry, I think I have those cases backwards. This one should be 0, right? Because if I started with character 0 here, then that would be H. Yeah, this was backwards. I'm sorry. I think I was traversing these in the wrong order. So this would have to be I minus 1. Reason being, we have to start, if this is the character in the front here, then we have to start with O, and then this would have to be LLEH, right? So we would need this to be the S sub length minus 1. Did I make the same mistake on this one? So this would have to be this would have to be H, and then this would have to be OLLE. So this would have to start at length minus 1. Oh, which it does. Yeah, that's fine. No, this starts at 0. Yeah, I'm sorry. I had these conditions flipped. So this would be the length minus 1. It's 1, and then we'll just return I. Sorry about that. I had those flipped, but hopefully that's clear that we start with that, because the first letter I would need on this one would be the H, right? That's the ending character if we start with this side. So I need the first calling part to be length minus 1. Or sorry, it's to be 0. Because the first thing I need at the end is to be that 0. So that should be a 0 there. Sorry, that's my bad. Is that alright? I'm sorry if I wasn't clear on that. I had those reversed for a second there. Okay, but anyways, let's go back to that. And if you have a question on it, stop me. But I guess the idea with this tail recursion was that we are going to start with the O at the end, and then we want this to return the ELLH part, right? So we want it to be the verse for the next part. So what we do is we have it call, actually with the 1, I guess. No. Length minus 2. Maybe we should start at the top too. So this is some sort of call in maybe main. And it gives us this. So when I go and call it the first time, what's going to happen is it's going to go, and it's not the base case, right? Length minus 1 isn't going to be equal to 0. So it's going to take the first character and add the function call to the right here. And then so it'll take the character and then it will do the function call. And then this one will take the next character, so the character at length minus 2, which would be L in that string. And then we said it's going to do a minus minus. So it will then take rev t. And then length minus 2 minus 1 would be hello. And then length minus 3. And then this here is a function call, so it's going to go and it's going to execute some code. And then in the context of that function, it's going to take the next character, which is L. And then, again, it's going to keep calling itself because we're not at the base case yet. And we said it's going to keep getting smaller and smaller. And then eventually it hits the base case. So at this point, I guess we know that length was originally 1, 2, 3, 4, 5. So length was equal to 5. So on this one, we called it with 5 minus 1, which is 4, 5 minus 2, which is 3, and then 2, and then 1. And then once we get to this last case, then we know that we should be good. So we've gotten O here. Maybe it helps if I write that above it. So this one, because the length is 5, this would be 4, this would be 3, this would be 2, and this would be 1. And so when we receive it here, it will actually be 1, so I guess I need to go back and check that really quick. And this one will receive it as 4. This one will receive it 3. Yeah, sorry, if it's not clear, this one's actually going to receive it at 0. In this case, the I it receives would be 1. But this will be 0, like the case that we had earlier. So actually, this is going to have that base case, and we said that when it gets the base case, all it's going to do is return the last character. So if we kind of work our way up, you can see here. Oh, no wonder it's not the right order. I saw the 2 L's and I guess I got confused. There we go. So this would be rev t. Hello, I'm sorry. Hello, length minus 5. And in this case, this should be the E then, right? I'm sorry, I forgot we were going backwards. So this would be the E, and then we'd have one more function call, which would give us the H. So, sorry, this is going to, I was right originally. This is going to call it with 0 then for the length, because we said the length was 5 originally. So this one will call it with 4. So it'll get the position at 4, which was O, and then this one will get the position at 3, which is L, and then E. And then on the last one, we're just going to get the H. So this one would be the base case here, right? When the parameter we receive I is equal to 0, we just return H. So what will happen is it will come back up here, and then one by one it will append these. So it will take the E and then put the H at the end. And then this one, since this will return the EH, it will take this, which is the EH, and append the L to it. And then when this one returns, it will take the LEH and append the L to it at the front. And then this one at the end will take the O and append the LLEH at the end of it. And then once that's done, it returns it back to main, and it's all the way reversed. So the key here is that it does the function call after this character actually has something done to it, which is just really nothing. It's just it's waiting to actually append with the plus. Is that clear? And sorry if I got sidetracked there for a moment. This should be right now. So the length was originally 5, so when we call it with length minus 1, this gets 4. So this is that S sub I, right? Then we worked our way backwards. Again, any questions on that? And I apologize if I got a little sidetracked, but that should be good, and I'll post the images on Canvas as well. So with the other function, which I won't write out, but you can probably imagine what the tree would look like, is it would do the opposite, where this character would start as H and then kind of work its way through the string, and then this would be the one that's calling the function every time, right? The reason I mention something like this is because if we had something like that Fibonacci function that we wrote last time, then when there's 2 function calls or more in some sort of recursive function, then you have to consider that functions get executed from left to right on a line. So if your function actually does something that may have some sort of side effect that affects your actual program, then you have to consider that it will always call the one on the left before it calls the one on the right. So something like that, you have to consider that it will go all the way down on the left before working its way to the right. And maybe we'll do an example of Fibonacci in a little bit just to kind of see that. But does this make sense with this call order, that it's always going to do the right-hand side until it hits the end? Versus the other one where it would start with the left-hand side, which is the head. So there's a distinction there. Right, so I think the other part of recursion that I wanted to talk about was just sorting a list, because I know that's going to be on the recursion assignment, so I figured it would be a little helpful to talk about it. And then maybe we'll talk about invariants. Okay. So last time I had to rush it a little bit, but we started talking a bit about sorting a list using recursion. So let's just say I have a list of, let's just keep it as 4 for now to make it simple. 0, 1, 2, 3. And we'll just put in here maybe 4, 7, 3, and 2. So we were starting with the idea of, well, maybe one way to sort this would be to use selection sort. So what selection sort does is it goes through and it starts at the beginning of the list, I less than length plus plus. And then we'll just say for j equals 0, j less than length minus I, j plus plus, and then what it does is it finds the max somehow. So the way we would do that normally is we would just do once over with the list, so we would go from there to the end and figure out which one of these is the biggest, and then it puts the max at the end, right? So we would find the max, and then we would swap the max with the end. So realistically, if you were to actually implement this, you would probably have some sort of variable that's just the max. So I would say something like, int max. I would maybe set it right here to be whatever element sub I or whatever, and then I would go through this and see if this is bigger than it, then that's the new max, right? And then we would maybe keep track of the index or something like that. Or maybe even just keep this as the index, that's okay. So that's the general idea as far as selection sort goes. So if I was to just do this off to the side here, then let's go through what a run of that would look like. And we don't have to worry too much about what the code itself looks like. Let's just do it by thinking about what it does. So for I equals 0, this is going to find the max of the list so far. So in this case, what is the maximum out of all the elements in this list? So it looks like the biggest one out of this list is the 7, right? So what the selection sort does is it's going to swap whatever the biggest one is and move it to the end, right? So what our list will look like after that is it will be 4, and then the 7 is going to swap with the thing at the end. So the 2 is going to be here now, the 3, and then we have the max, which is 7. So this so far, we could say confidently, if we've moved the max to the end of the list, then the max is for sure sorted. And then if we go to the next one, we would look for the max in the rest of the list that's not sorted. So this part right here would be the unsorted list so far. So we can't be guaranteed that this has been sorted because we've only sorted the max by doing one run through. So the next thing we would do is we would look through the max and find it in this unsorted list. So here I would say 4, 2, and 3. What's the max out of those ones? Well, it's definitely 4. And we would go and we would swap 4 to the end. Oops, not the color I want. So I would swap 4 with the end of the unsorted list, which is currently 3. So we get 3 there, 2, and then 4, which is now sorted. And then the 7, which was already sorted. So now that's the sorted part of the list, and this is the unsorted part. And then for the next one, we would do I equals 2. And then the max equals, so out of this unsorted list, the max between 2 and 3 is 3. So we move the 3 to the end. We have this sorted part. And then we have the 2, which is technically sorted, but we don't know that yet. And then we go to the next one, I equals 3. And then we can say just by the fact that it's a length 1 that it is sorted for sure. We'll just say the max is equal to 2. And now the whole thing is sorted, right? We can verify that everything in the list is for sure sorted because we ran out of things to actually try to sort. So the idea is that we move the max to the end of the list every single time, right? Right, so let's try to do this recursively. So what we need to do, you'll notice that we kind of have something like what we had before, where we actually have a tail, which is the sorted list, which is actually something that we have right now, and then we have the unsorted list. So we want to actually maybe recursively do this, because if we think about it, recursion, again, it uses some sort of pre-solved condition to solve this new case. So if we had a list where the last part was sorted and the part before it is not sorted, then what we need to do is we need to sort that part before it, right? So I maybe want to sort this list that's 1 smaller than the current list, and then if I do that enough, I'll eventually get up to a point where the list is sorted because there's nothing left to sort, if that makes sense. So if we manage to keep getting to a state where we sort one at a time, then the list will eventually run out of things until the point where we know that the whole thing has to be sorted. So what we'll do here is we'll say void, and we'll call this recursive selection sort. And as per usual, we'll need to take some sort of index. So we'll take here an array. I guess it's an integer array. So we'll say integer array. Or are that to use a swap keyword, or do you want us to make a temp and swap? I don't think there's a swap keyword in the language. Some languages have an operator for it. I guess I'm just writing that generically. So that would be those 3 lines that we wrote for the first week for bubble sort. That's like, temp equals temp something, temp equals the first thing, and then the first thing equals the second thing, and then the second thing equals temp. What I do recommend is maybe just generically write, you could even do it with templates if you want, write a function called swap that does it, or you can write the 3 lines if you really want to write it. I guess I just generically, and you'll see if you are a CS major and you keep taking these courses, a lot of people will write just some function that does some expected thing, just expecting you to know that it works, I guess, if that makes sense. So there shouldn't be a swap function in C++, at least I don't think there is. I guess I'm just writing it as a, hey, you do this sort of thing. But you can write a helper function called swap. I think that maybe makes it easier to read. And I guess the same sort of thing with max. There's no function called max here. I'm just saying write a function that finds the max of a list. Or, write the equivalent code. So let's just think about what this function should do. So the first thing I think that helps to think about when writing a recursive function is, what is it supposed to return? Well, this is supposed to return the list. In this case, we called it R. Returns R sorted up to index I. Or you may also see it written as sorts a list of length I, which is fine as well. Just consider if you're giving a length, then we know that length minus 1 is always the end of it if you decide to write it that way. I just prefer to write it with indices. So what we want to do is we want to take each of these and sort just the thing at the end of the current array. Right, so in this one we were sorting this part, and on the next level we were sorting just this part with 2, and then on the last one we were sorting a part with 1. So again, we're going to need some sort of base case and then some sort of reduction operator. When doing sorting, I think the most common sense base case, and you could do multiple, especially if you ever talk about quick sort, which they usually go over in 302, and merge sort, I guess, for that matter. We could have multiple stopping points. In this case, I'm just going to say, because we're subtracting by 1, it's safe to have one stopping point, which I'll say is if I is equal to 0, since we're talking about indices, then we'll just return. So this is void, so I can just return it straight up. I guess I need to make this by reference, right, if I want this to actually modify the array from the last call. Maybe I need to make that a little bit bigger. So that would be this case here. If we had I equals 0, we could do some sort of swap, but it doesn't really matter, because once you've gotten down to one element, which is when I equals 0, when it's pointing to this one, then we know there's not anything left to do, because if you have a list of 1, then by definition, a list of 1 is already sorted. And also, if you're thinking about it, a list of 0 is sorted by default too, because if you think about a list that has nothing in it, then by just virtue of existing, it is sorted because it's not out of order. So if I have a list that has nothing in it, it is really sorted. And you'll maybe think about that base case if you do merge sort or quick sort, which we won't talk about here, but if you're ever curious, just ask me, and I can talk about it. But we'll just say if the length is 1, then it is sorted, because that is by definition true. And we could also say the same thing about list 0. Right, so if it's not that, then we know we actually need to do some sorting. And again, I'm just going to write some pseudo code and kind of wave my hands, but we'll say find the max. Up to I. Since we know the length of the array that we have is up to I, that's the last index, and then we will swap that to the end by definition of what selection sort does. So it always moves the max to the end of the array, since that's where it needs to go. Right? So swap with the end of the list, which would be R sub I. Okay, and that's really all we need to do as far as that sorting part goes. So this will always move the max to the end. And then what we need to do is we need to sort the array for the next level, which is this array that's 1 smaller than the one we currently have. So if I wanted to do that function call, then I know I'm going to call this function itself, recursive selection sort. And I'm going to call that with the array, which is, again, R. And I'm going to do it on the array that is 1 smaller. So I'm going to move the index back by 1, which is the reduction operator. So in between the reduction operator and the recursive call here, and the base case, we might also have some extra code that might need to do something like this part. So it's reduction op, and this is the base case. At bare minimum, whenever you write a recursive function, you will need these two things. And I'm stressing that a lot because it is kind of important to consider. But we can have other stuff. So I can do this extra code here that actually does the sorting part, because I kind of need that. Right, so this should work. This should actually sort an array. And I think maybe we'll just write it really quick so that we have it, and maybe so that you can have it for reference when you do assignment 9. Because you will need to do both the reversing of a string for that one and sorting a list. I know I threw both of those in there. And then there's one recursive thing that I'm not going to write, I guess, that you'll have to do for that assignment. So if we go up here, let's just write a function void. Maybe we'll do it on a vector. So we'll we'll say recursive selection sort. And we'll do it on a vector. Let's just do it on integers, but we could do a template type like we learned last week, and that might be helpful. And I want this to be by reference, and then I'm going to pass in an integer. And I need to include the vector library in order to do this. Alright, there we go. And we'll just write that down here. I'll just call this list for the time being, and then we'll say int I. So we'll say if I is 0, then we just want to return. Else we'll find the max, which we'll just write the code for that really quick. So I'll say int j equals 0, j less than I. We'll say less than or equal to I. Since this is an index, then I do need to go to equal, which might be why you write it as a length instead when writing it j++. We'll take an integer max and we'll set that equal to list 0. In that case, I guess we can start counting at 1, and then we'll say if list j is greater than. Actually, let's just do this as an index. I'm going to do this as 0. Max equals 0. Max index equals 0. So if list sub j is strictly greater than the list at the max index. So if the current element is bigger than the max, then we know that it should be the max now, in which case the max index will be equal to j, and that's really all we should need. So now by the end of this, we know that max index is going to represent the index of the maximum, and then we just need to do the swap. So this would be the swap part. Find max, and then we know when we do that, we typically make an int temp, and we set that to be equal to one of the two things. So let's just say list sub I, and then we say list sub I equals list sub max index, and then the list sub max index is equal to the temporary variable that we stored. And the other convenient thing about this is that if the max is already at the end, it will just swap it with itself, which does nothing. So this can be a little bit helpful because we don't have to do any extra if checks and make sure that we're not swapping it with itself. If we do swap it with itself, it's not really a big deal, right? It'll just do nothing. So then sort the smaller sublist. So we'll just go here and we'll call recursive selection sort, and we'll do it with the same list that we've been operating on, and then we'll make it size -1. Right. Let's just make sure this works up here. So I'll make a vector of integers. I'll call it int list. And then let's just push some things into it. So we'll maybe push the things that I wrote here. So we started with the list 4732. So push back 4732. Maybe let me zoom in on that a little bit. Right, so we'll push all that in there, and then we will call recursive selection sort on the integer list, and we'll call it with size integer list dot size -1. And then here we'll just print it out to make sure that it's correct. So int I equals 0, I less than int list dot size I plus out int list sub I, and then we'll just do an end line in case we decide to do more. Alright, let's make sure that this actually works. Hopefully, fingers crossed, we did everything correctly here. And we'll see that it does print 2347. So it printed the list 4732, and it sorted it. And then this was just our for loop from last time. Actually, I guess I should zoom in so you can see it, but yeah, it does print it sorted. So that's great. We can sort things with recursion. And you'll find out eventually, if you learn about quicksort or merge sort, that actually if you do it recursively, you can do it way, way faster than we do with something like bubble sort or selection sort here, which are kind of slow, but maybe just easier to understand. Any questions on how we managed to get that to work? Again, I'll show it really quick just in case you need to take a look at it. Alright. I don't want to start on the next topic yet, but I do want to talk about one more thing, I guess, before we go. Maybe a little bit more. Really quick. Let's talk about invariants, which can be a little bit hard to wrap your head around at first, but it's kind of important for the sake of problem solving. Perhaps it would help if we did it with the functions we wrote here. Let me go ahead and let's take this here and we'll add it to a new page. Right. Let's write that a little bit nicer than that. Let me write out the actual full C++. So if I wanted to do this string reversal thing, then, oh, you know what? I actually already have the code on Canvas. So we have this code here that, let's just look at this one, I guess. It takes the string str and it reverses it. So it always stores it in this variable reverse1, and it appends the next string to it. Okay. Actually, maybe it's easier to think about this one first. So let's take a look at this function. So this function, I don't see the scroll bar. There we go. So this function takes the string and it goes from the start to the end, and every single time it takes the current character and appends it to the front of the other one. So when we go to execute that, we ended up with something where the order of execution looks something like this, right? So the string at each point was equal to this red part. So we could say that it's the empty string right here. If we take a closer look at the actual reverse 2 that we have every single level, then we can make kind of an important distinction about it when we compare it with the I that we have. So this was I equals 0, 1, 2, 3. If I was to make a general statement about this input, in other words, or not input, but this variable that we have here, so this being the reverse 2, and this being I, I'm going to write this on a different one. I don't want this to be super cluttered later. Let's just remember this was here, and I'm going to write it on a different page. So let's say reverse 2, 0, 2, 4. Let me maybe make this a little bit wider. So we know when we start the loop, reverse 2 was just the empty string, and then on the next level it was H, and then it was EH, and then it was LLEH, and then it was, oh, whoops, adding one too many. LEH, and then it was LLEH, and then at the very end it was at 5 LLOEH. Right. So do you notice any relationship between I and the string on the right? Is there anything that they have in common, or that I describes about the string on the right? And you could say a bunch of different things, but any observations that anybody has about it? Total number of letters, right. Good observation, that's part of it. Yeah, we can work off that, so that's a good idea. So it's the total number of letters in the string. That's definitely right. And another way of thinking of it is it's the index in the original string so far, which I guess is what I was by definition, but it is also the length of it. So one way we could describe the relationship between these two things is that rev 2 is the string up to I, or of length I, reversed. And the key to that is that this is what is the result of that for loop after every single iteration that it does, right? After every single loop through the whole thing. Right? So at the end of every single loop, which is only one statement here, but at the end of every single loop, we know that reverse 2 is going to hold the reversed string of length I, or up to index I. And we know that should be true every single time we finish the loop. And that's never going to change. So when we do something like that, this is what's referred to as a loop invariant. And a loop invariant could be a bunch of different things, but it's just a general statement that you use for problem solving, that you say, this is the thing I never want to change while I'm doing my code. So I call it a loop invariant here because we actually use the physical loop, but when you're doing something like recursion, you might just call it your invariant, or your condition, your precondition or postcondition or something like that. But the idea is that it never changes. We expect when we start the function, or start the block of code that we're going to execute, and end the block of the code of the execute, that this statement, this general statement that describes our function or our code, is going to be true. Let's take another look at the recursive selection sort then. So if I was to come up with some sort of loop invariant, or just invariant because we're doing this recursively here, then what I might say is that the list with I many elements is sorted, right? Is that by the time I get to this point in the code, which is the beginning, and this point, which is the end, that it's true in both of those places. It doesn't matter if it's not true sometime in between. So when I'm doing the swap here, I'm not necessarily going to be having it sorted, and you would see that would be especially the case when we do something like bubble sort, where it actually ends up moving some of the things back and forth a bunch. But when I start this function, the list up to that point I is going to be sorted for sure. We know that this here, this being the I, is how many things have been sorted. So I guess in this case I plus 1 with the way I wrote it, but here one thing is sorted, here 2 things are sorted, here 3 things are sorted, and here 4 things are sorted. So my invariant for this is the I last elements in my list are sorted. And the key here is that that's true after the beginning and end of every single part of this execution. So an invariant is something that you don't want to change, and it's important to think about when you're writing something that does loops or just trying to problem solve is, this is my goal, this is the thing that I want to be true when I start it, and by the time my code is done, I want this to be done at the end. And the problem with this is that it's kind of abstract. There's multiple different answers, and possibly some of them are right, and it's just kind of a matter of choosing a statement that makes the most sense and is general enough but specific enough that it describes your problem, but doesn't describe too many variables at the same time. And I think this is maybe a difficult concept to work with, but if you start to think about it a little bit, problem solving when you're actually doing coding kind of becomes easier if you use this paradigm of what am I trying to accomplish, what do I need to have done at the end of every single loop. And you can have multiple invariants if you have multiple loops inside of one another, and so sometimes I think breaking up a problem like that can be kind of helpful, where if I was to do something like bubble sort, then I know I can have multiple invariants. So maybe we'll just end on bubble sort really quick, and how I maybe will do the invariants for that, and then we'll leave it at that. I don't think, just to throw it out there, I don't think we're going to test on invariants, but I think generally this is the place where we should talk about invariants as far as computer science goes. And somebody might bring it up later if you take like an algorithms class or something like that. And you'll see I actually write a lot of invariants in the sample code that I give for some of these. Just throughout the class, I'll write invariants by the top of a for loop just to keep clear as to what it should do. So I less than length I plus plus. Yeah, so j less than length minus I. And then we do the if out of order swap. Again, just writing pseudo code, we're just going to assume this is whatever is correct. Right. So we have two loops here, and so we have two invariants when we actually do bubble sort. So if we consider what bubble sort does, is the outer loop is how many things have been sorted at the end, and the middle loop is the part that actually does the bubbling. It kind of like swaps things as they go up. So the invariant for this one, for this outer loop, would actually be the same as selection sort. So it would be something along the lines of I last elements of the list are sorted. And then the other one, I guess, is a little more ambiguous. Actually, I suppose it might be the outer one, right? Well, yeah, well, we know when we get to the beginning and the end of that's true. In the middle one, we could make a bunch of different sweeping statements, but the idea with bubble sort, right, is that you always move the biggest number to the end. So maybe if I had that, I would move the biggest number to the end, and then that's always true by the end of it. And we also know that after every single loop, similar to the selection sort, that the I last characters in the thing are actually sorted. So maybe for this one, and again, you could probably give a bunch of different answers. The outer loop, I would say something like the last elements are sorted, and then I would say that the max maybe is at, well, actually, this one's going to loop over the whole thing. No, I think that's not fair. This one's a little general. So this one's actually just swapping between two things, right? See, this is what I mean by invariants. It can be kind of hard. And this one maybe isn't even that useful. Well, I suppose we could say that the j and j minus 1 or j plus 1, because we usually look at the left and right, are in order. Since we know what bubble sort does is if j and j plus 1 are in the wrong order, it swaps them, right? So maybe that would be one way we could phrase that sort of invariant there. So you can have multiple invariants, and sometimes maybe thinking about the invariant is actually harder than just writing the code, but I think it does help some of the time when you're doing problem solving for really big pieces of code that have 4 or 5 for loops, that it's important to think about what needs to be true before and after. Alright, but I think that's about all we have to talk about for today. If you have any questions, just let me know. If not, I will see all of you on Wednesday.